Ray, you can start when you're ready.
Okay. Okay. Good morning, everyone. Today I'm going to present a paper titled Bridging the Generic and the Personalized Federated Learning for Image Classification. And this is the paper that published on ICLR this year. And here is the outline. So first I will talk about this motivation. In the standard federated learning, we all know that the generic goal is to introduce multiple clients to collaboratively train and find a single global model that can perform well on the genetic data distribution, such as the union client data D. And to achieve such goal, we can formulate the optimization problem as follow. So we try to minimize the global objective loss at the capital L as the weighted average of the local empirical loss. So the DM represents the local data set and the capital LM represent the local empirical loss. So trying to minimize that, we find this optimal global model. However, as we can see in this framework, we have multiple clients, and each client may have different data distribution as different local data sets. So one of the key challenge in the federated learning is the non-ID distributions. So because of this non-ID distribution, we can see when we do the local training, the local model of each of the clients shift away from the global models, and the resulting aggregated global model is deviate from this true optima. So because of the non-ID data, the test accuracy actually could be dropped because of the training based on the federated average and the original objective function formulated as this equations. So we can see the accuracy drop because of the resulting global model actually is a suboptimal solutions. And to solve this problem in the genetic setup, the existing work is trying to reduce the local shift by either modifying the local objective or designing a new aggregation rules to improve the global model performance. But even with improving the global model, a single global model is not able to perform well on the client local set because of the non-ID distribution. As you can see in these figures, the original square represents the client optimal with respect to their local data set. So it is very difficult to find a single global model that have the uniform performance on the client local test set. So another line or another setup for the federated learning is called the personalized setup, which instead of sticking to a single global model, we are going to construct a multiple customized models. And each of the personalized this model can perform well, specifically focused on the client test data. So in the non-ID settings, we actually can have two lines to solve the non-ID issues. But because of their usually target at different scenarios, for the genetic one, we focus on the genetic test set, for example, like the unit of the client data. And the personalized, we are more focused on just the single client local test data. So far, these two federated learning setup are developed independently. And in this paper, they find out that actually these two goals can simultaneously achieve. And based on this key observation, that's the personalized model actually seems to come free from the local training of the learning algorithms. So if we take a look at the global, the generic federated learning accuracy, the global model is no doubt outperform the local models. But if we using the local models in the federated average to test on the local test data set, we can see that actually the local model has a very good performance and outperform the global model in the federated average, which means that we actually can use one algorithm to achieve two models that can satisfy the goals in the GFL and the PFL respectively. And based on this key observation, they're trying to propose a unified framework that can simultaneously achieve a robust global model and a strong personalized model that has the decent personalized accuracy in terms of each client's local data.
Ray, I have a quick question here. It seems they're trying to find something in the middle, right?
No, I think they can achieve both goals. They do not trade-off.
This is two facts, right? For global model, definitely, you consider the union of clients' data. Global model is better than personalized, the local model, right? But if you consider specify to personalize the data or distribution of each client, personalized federated learning model definitely is better than the global one, right? Because it's more personalized. So are they trying to combine these two, find something in the middle, or will we adjust something, say, kind of satisfy both? Yeah.
Yes, I will introduce later. They actually can satisfy both because of their new algorithm.
When you talk about both, is it both with a better performance, or it's kind of like I said, it's kind of like a trade-off?
No, both with better performance.
Oh, okay. Move on, please. Thank you.
So next I will introduce their proposed framework called the Federated Robust Decoupling. So to achieve the global model and the personalized model simultaneously, actually, what they do is they decompose the local model dual duties. Here, figure shows the local training model architectures. So they actually designed a two branch to achieve the two goals. For the generic federated learning, this is followed by the first branch. They're actually trying to obtain a accurate and robust global models by introducing a feature extraction followed by a G hat. Usually it's fully connected layers. And the output is the predicted logic. So in order to update the parameter in the yellow box, they use the balanced risk, which replaced the traditional empirical risk to improve the global model accuracy. And the second duty is they want to serve as the personalized models. So on top of this feature extraction, they were introducing a lightweight predictors that called the P hat, which were trained by the client empirical risk to achieve the high personalized accuracy. So they designed this two predictors framework to achieve the both high global model and strong personalized models. And I will introduce each of the module one by one. So for improving the generic federated learning, we can see the traditional federated average, the objective function is formulated in here. Because of the non-ID distribution, or specifically the non-identical class distribution, to minimize the empirical loss of this capital M is not consistent with minimizing this capital L. So to improve the accuracy, they follow the idea that they're going to modify the local objective functions by setting a consistent goal that each of the local, that the learner model should classify each class well, so they can treat the local training as an independent class in balanced problems. And yes, they just directly leverage the standard formulation from the class imbalanced learning problems by replacing this LBR with the balanced softmax loss with the traditional empirical loss. So in this way, all the clients are trained with the consistent goal so that they can improve the global model's accuracy. And the second one is they trying to deal with the personalized federated learning. To do that, as we see, the local model from the federated average actually can have a very good performance and in terms of the high personalized accuracy. It's because of the following secret ingredients. If we take a look at the local training for the traditional federated average, we try to obtain the global model by minimizing their local empirical loss. At each round, in the beginning of the local training, we will initialize with the average the global model parameters. And they find out that actually this minimization is reflects an implicit regularization terms that will help to improve the personalized accuracy. So they compare the local model in the federated average with the personalized framework called the detour. This is the one of the personalized model that using the regularization terms to improve to obtain the high personalized models. And as you can see in the detour, the local training actually is the empirical loss plus the regularization terms. And the initial for each round, they will do the gradient update based on their local model. And this big omega is derived from the global information. And if you can see these two terms, actually the reinitialize the local model with the average of global model parameters actually is imposing the L2 regularization, where we can see the big omega is the W bar, and we set this lambda equal to infinity. So we enforce the beginning of the training, we set all the WM equals to W bar and do the training. And during the training, the lambda will become smaller to 1. Oh, sorry, smaller to 0. So in this case, actually the initialization with the weighted average is the strong regularization terms in the traditional federated average. And they do the empirical experiment to confirm their assumptions. They compare the empirical loss in terms of the local loss functions and also the regularization terms. As you can see, because of the detour do not reinitialize every each round, so the empirical risk actually has a smaller loss in the detours. But in the second terms for the regularization, we can see that actually reinitialization with the weighted average, it can achieve a very small value of these regularization terms, and in turn out can have very good performance of the personalized accuracies. So you can see when we compare the training and testing accuracy for the personalized and the federal average in the non-ID settings, we can see that the local model in the federal average actually is outperform the detour in the testing data. So in this case, to obtain the personalized model, we do not need to do any additional design or introduce any additional regularization terms during the training. What we can do is to reinitialize the local loss with the global or with the weighted average is already serve as the regularization's impact. So
if my understanding is correctly, they're saying federal average is good enough, right? So we don't need to do any
personalized model, yes.
For personalized, yes. For personalized model is good enough. We don't need to, add the extra regularizer, right?
Yes, because of the initialization. Yes.
Yeah, I mean, what it means, the procedure of the federal average is the same, has the same impacts as, the initialization with the global model, with the W bar or something, right? Okay, so we don't need to do any extra operations. We just keep the general federal average procedures and the steps. That's good enough for personalized federal.
Yeah. Yes, actually,
okay.
I also see the accuracy for the local model in the federal average. It's like outperform others personalized models.
Can you go back to the previous slide? Here, do you mean that they want to say if you use the federal averaging, you can obtain this W bar, then you can just solve this optimization problem by getting you can solve this optimization problem, and then you will be able to get a personalized model.
Yeah, because in the federated average, we have the local model after the local training. And but usually we just focus on the global model, but they say that actually the local model in the federal average is already a very strong baseline for the personalized model. Yes.
So are they going to, because this is round by round, right? Let's say you have 100 rounds, then are they going to use the, for example, the personalized model, this WM in the last round, for example, in the 100th rounds, to serve as a personalized model?
Yeah.
Oh, really? Okay. I see.
Yeah. Also, you can see from this figure, for each round, they will do the evaluation for the personalized data set. And you can see over round the local model in federal average actually is outperform the detours testing, the detours model.
So what's the y-axis here?
Here is the accuracy.
The accuracy on
the client local data set.
Okay.
They test for the personalized model.
Okay, I see. Interesting.
Well, if in that case, it's kind of overturn. I would say not all the federal personalized federal learning design, but at least it's going to overturn many of them, right? That's what you're saying.
Yes, it's what I think is their key observation and difference here. Yes.
That means those personalized federal learning designs, most of them doesn't make much sense. As long as I use the federal average, I can beat them. Okay.
Yeah, because for them, they only consider the global model for federal average. They ignore the local model for the federated average.
I mean, they're talking about the non-ID case, right? So
Yes, the non-ID case.
for ID case, probably it's not the case.
For
Personalized
ID
design
is the same. For
is
the
the same.
the local, they are follow the same distribution.
Mm. They empirically do that or they prove that?
They empirically do that. They just show that because of the regularization term is very small. Also show that the variance of the gradient is also very small. I will show later in the experiment. Yes, they
Okay.
are very small compared with other personalized model, so that they actually the initialization with weighted average is very effective.
Okay.
Just show that there's no theoretic proof.
Yeah. Okay. Sometimes do nothing is better than to do something for the machine learning. So okay, okay. Interesting. Thank you.
Okay. So in this case, we have two laws, which the first one is the generic model that we have the following parameterized. First, the theta denoted as this feature extraction, most like the CNN models, and the generic prediction hat as the phi here. And these two model, the parameter of these two module will also do the weighted average over the server size. It's similar for the federated average pipelines. So using the balanced risk, we are able to improve the global model accuracy. But for in terms of the personalized model, we should learn we should let the model to learn the empirical loss over their local loss, local test data. So here we still using the empirical loss for the personalized model, and to update the personalized prediction hat, he had the parameter here using the empirical risk.
I have a minor question here. So using the balanced risk metric to improve the general file learning performance, is this their contribution or is kind of
it's
their
kind of, yes, they treat the local model as the class imbalanced one.
Jiahao, are you there? You're an expert in ERM,
Yes.
right? Is there any reason you can justify if we use a balanced risk is better than empirical risk, and why, previously nobody have mentioned that in the literature?
No, Darpan, because I don't understand what is the balance risk. And this is the first time I heard this term.
Okay. Okay. Yeah, probably we need to look more into this. Okay. Thank you, Ray.
Yeah.
Okay.
Thank you, move on, please.
Okay, so so the overall training process is as follow. So they generally follow the federated average protocols. So in the client side, it would have a local training objective as the summation of the the balanced risk plus the empirical risk. And in one single forward and password, we are going to derive the gradient of the parameters, which from the feature extraction and G hat using the balanced risk. And also for these two terms, we do not derive the gradient in terms of the empirical risk for the personalized models. So we can derive this three gradient and update the corresponding parameters and send the theta m and the phi m to the servers, and the server will do the weighted average and send back the global model to the client to the further training. And here is the overall framework. And there is a small extension for their work is that in the previously, we can see the introducing this personalized prediction hat is a static one. And they can further extend to a meta learnings. We introduce a meta models that to learn this prediction hat with different client class distribution. So in this case, they can easily adapt to a new client and also to do the future training for any new clients using the meta learning. And the local training for the personalized model will become to minimize these parameters. And also because of the meta learnings, so we also train this using the federated average. So that's this the HyperNet using the design here can adaptively output the personalized prediction hat with giving their local class distribution. It's a small extension for their proposed methods here.
So how do they define this balanced risk? I just may miss that.
Balance risk. Yeah. I will show. You want to see the formulation, right?
Yeah.
Okay. Yeah, here is their formulations. So I actually just borrow the methods from the class imbalance learning problems, and you can define the balanced softmax loss as here. The N represents the number of the data in the class C or the class Y here. M is the user's index. Eta is a hyperparameter. Here is like the balanced softmax loss.
So basically, what they are doing is so you have imbalanced class. So I'm trying to sample more examples from the minority class, right? So that the resulting samples, they will be more balanced in terms of.
And like put more weight in the minority, trying to balance the weight among different classes.
So for this imbalanced class, I mean, imbalanced class looks like this is not this is not the only example for long ID distribution.
Yes, you're right. So they only consider the class imbalance problem. In the 9D condition, actually, we're facing three scenarios. One is the imbalanced class. One is the class conditional data distribution or the joint one. So they only consider these cases. And they say that because this one is very difficult to design a constant goal. So they only focus on this imbalanced class case. Yes.
Okay. Yeah. I get a point here. So they have different distribution, this PMXY, because this PMXY, they can be decomposed in two parts. They just say the first part is the same. They assume it's the same. So they focus on the second part.
Yeah.
Okay. I see. Yeah, it's very specialized. Yeah, looks like it's very specialized here.
Yeah.
Okay, I see. Thanks.
Okay, so next I will show the experiment results. So here they consider a convolutional networks, and the dataset they use is the Cypher 10, Cypher 100, and the Fashion Minist and the E-Minist dataset, which are the typical federated learning dataset they use. And for the non-ID settings, they consider using the richest distribution to generate the different numbers, the imbalanced numbers and the imbalanced class distribution for each client. And here is the client settings. They also consider the partial participant in their experiment. And next is, here is the evaluation matrix they use to show the performance. For the generic performance, they use the global model called the GM on the standard balanced test data. So the average will be the average over the test samples. And for the personalized performance, they're using the same test set, but they are reweighting the accuracy for different class based on the based on the PM for different clients. So they reweighting the accuracy to show the performance. They claim that they do that to avoid any variance due to how to split the personal test data set. So they instead they do this way and calculate the accuracy in terms of this, and they would average all the clients' accuracy to show the final results. And here is their overall performance evaluations. So they have 4 different data sets, and they use the different non-ID settings. For the writers, they just consider each writer has their own styles. And for the parameter here, the 0, 1, 0, 0.3, the large value means the data is more IID. So you can see this row show the existing method that proposed to improve the generic federated learnings. And this row show the method that aim to improve the personalized federated learnings. And compare with all this existing work, you can see that the proposed method either is compatible or even outperform the existing methods. And interesting, you can see for the testing set for PFL, the personalized model in the federated average actually has a very good performance in terms of those personalized methods. And next, they further do the evaluation on the initialization with the average. And here they show the impact of introducing the balanced risk loss function. And as you can see, the dot represents the local models. And the line here is after they do the weighted average. You can see that the proposed method is more smooth and have a high accuracy. And also in terms of the gradient variance per communication round, you can see the proposed method have the smallest variance, and that implies the better generic performance. And next, they will show the decoupling things actually can help to achieve both high high accuracy in terms of the generic federated learning and the personalized federated learnings. And as you can see, if we replace the traditional empirical risk with this balanced risk, we can show that the performance of the generic accuracy actually higher, but the performance of the personalized model become less compared with the federated average. However, if we just decouples the two duties, both of the proposing methods have maintained a high global models, global accuracy, and also a very high personalized accuracy. Okay, and then they also show the the effectiveness of different the prediction hat. And as you can see, the generic prediction hat can generally perform well on the different on average client data set. But if we introducing the personalized hat, we can see this diagonal line, the personalized accuracy actually improved. But in terms of others tested data, the accuracy will be dropped. And here they show the meta learnings is benefit from this future client. So they consider 100 clients in these settings, and 50 clients will engage in the training and 50 are not. So they do the experiment on the unparticipated clients, and to show the accuracy, as you can see, even without the fine tuning, they can already have a very high performance due to the meta trainings. And after the local fine tunings, they can outperform the others. And that's it. Here they have two key observations. First is that this strong personalized model can emerge from this local training due to this implicit regularization. And the second, if we impose a class-balanced objective function, can further improve the generic federated learning accuracies. So they propose this two loss, two prediction framework to achieve these two goals simultaneously and have a very high accuracies. And also the meta learnings module can help them fast adapt it to the new clients. And that's it.
Questions? But I think those two observations, are they coupled? I think they're separated, right? The one of them is just saying, okay, fair average actually has an implicit regularization, so it's good for personalized learning, right? Fair learning.
Yeah.
The other one is they just propose a new metric for the generic fair learning, right? So
Yeah.
it's kind of tricky to say you combine them together, but even you're you just separate them, they're good, right? So it's not necessary to say it's a two loss, two predictor framework. So, it's just two separate observations. Based on those observations, they derive something and propose something, right? It's not that coupled from my personal feeling. Yeah.
Yeah, but they're able to like design in one framework. But actually,
oh, okay. So one framework you can achieve both goals, right? So
yes.
let's say you have a generic FL task, you also have personalized FL task. Oh, okay.
Yeah.
Okay. Any questions?
Ray, I have a question. Could you
Yes.
go to the observation part?
The beginning?
Yeah. So given like these two figure, how to like get this observation, the strong.
You just say that
Yeah.
the local model they have a very competitive accuracy. They're just a very strong candidate for the personalized model.
Oh, that means like for the generative learning, they ignore the local local models. They just pursue the better performance on the global model. But for personalized is vice versa, right?
Yeah.
Oh, okay. I see. So how they they say the generative learning and personalized can be approached simultaneously. So this conclusion is based on observation or based on their algorithm, do you think?
I think it's first based on this observation. It's like when you finish the federated average, you actually have two models, right? The for local and the global one.
Yeah, but look at like
Yeah, just the global one, they have very bad, like they have very poor performance.
but you know the reason why people consider personalized learning is because the federal average is not good at the local model, right?
Yeah, it's because of this figure, right? On the right figure.
I think Jiahao's question, I'm not sure, probably I guess Jiahao's question is that because of you use the balance risk? So somehow
No,
you
the
shouldn't-
balance rate is for the left one.
I know. But you know, is this two coupled because of use the balance risk so that your federal average somehow have a better personalized federal learning performance as well? Because if you use this one, I believe this one you use the yarn app, right? Obviously, you know, if you use the federal average, the global model's accuracy. This is a testing accuracy.
Previous work, they only consider this blue line. They do not consider this orange line in either their motivation or in their evaluations. They only consider this blue line for the personalized model because they say the single global model cannot perform well on the client.
Oh, I see. I understand.
Okay,
Yeah, this sentence
okay.
makes sense. Yeah, that's the argument I hear a lot. Yeah. Okay.
Yeah. So that's they say actually this local model can do the things. We don't use the global model to do the testing. We should use the local model to do the testing.
Okay, thank you.
Any other questions? Okay, it's very interesting paper. I think at least I should go back to check the paper. I think everyone should go work on learning, should check this one. Very interesting two observations. Okay, if no, let's thank Ray. Let's wrap up today. See you guys next Wednesday, okay? Thank you.
Thank you. Thank you.